Hi, what's up guys? This is second session of this series and I'm going to solve another problem of Newton's viscosity law. Note that guys, I don't solve straightforward problems and I usually solve tricky problems. You can find a solution for simple problems, for straightforward problems in any fluid mechanic books solution manual. So I solve the problems which usually don't have solution anyway. Okay, let's jump to the problem. The distance between top and bottom parallel plates is h. This is top, this is bottom, and they are fixed. And the distance between two is h. Okay, the mid plate is pulled with constant velocity of v. This velocity is constant. Using force F and some forces pulling this plate. Okay, assuming mu1 over mu2 is a ratio of viscosity of fluid 1 over viscosity of fluid 2 is a. We are asked to determine h1 over h2 ratio of distances from top and bottom plates such that F is minimized, our force is minimized. For this purpose, we have two steps. The first step is to obtain a relation between force F and one of the parameters h1 or h2 such that F of h1 or h2 equals to some relation. The second step is putting derivative of F with respect to h1 or h2, then calculating value of h1 or h2. Okay, this is the process for solving this problem. First, let's look at the information we are given in this problem. It says that h1 plus h2 equals to capital H, and mu1 equals to a multiplied by mu2. We are going to use these information to solve our problem. Okay. I consider the velocity profile at the fluid 1 like this, and I call it u1, and the velocity profile for fluid 2, and I call it u2. Okay, u1 and u2. This is u2, and I call the coordinates for y1 from here and y2 from here. You may consider coordinates from any point you want. You may consider them from the mid plate or both from bottom plate, but this configuration and this arrangement for coordinate origins is the most useful one to solve our problem, I think. Okay, so we have tau1 shear stress imposed by fluid 1 at the top of mid plate and tau2 shear stress imposed by the fluid 2 at the bottom of mid plate. So tau1 equals to mu1 du1 over dy1. Okay, and tau sub 2 equals to mu sub 2 du2 over dy2, both evaluated at mid plate h1, y2 equals to h2, and there is associated force for tau1 which equals to tau1 multiplied by a, and also for tau2 is f2 equals to tau2 multiplied by a. What is a? A is area of plate, mid plate parallel to flow direction. This is our flow direction. Okay, now also from the previous session, you remember that U1 equals to capital V over H1 multiplied by Y1, and U2 equals to V over H2 multiplied by Y2. Okay? So from here, we have tau 1 equals to mu1 V over H1. And from here, we do have tau sub 2 equals to mu2 V, capital V, over H2. Capital V is the velocity of the mid plate. Also, we had mu1. Let's work with mu2. Also, we had mu2 equals to mu1 over A. So what do we have here then? Tau 2 equals to mu1 over A, capital V over H2. This is mu2 from this relation we had before. Okay? Now, we should draw a free body diagram for mid plate. So this is our mid plate, considering, okay, some F force pulls it and two forces resisting against that pulling force. Okay, now Newton's second law of motion. What does it say? It says that sum of forces in x direction, this is our x direction, equals to mass of plate multiplied by acceleration of plate in x direction. But since v, velocity of plate, is constant, we do not have acceleration, i.e. a of x, acceleration x direction, equals to 0. By this, we have sum of forces in x direction over our plate is 0. And writing one by one all the forces, pulling force minus force 1 minus force 2 equals to 0. This results in force equals to F1 plus F2. Okay, and this is, we had F1 and F2 before. This is F1 and this is F2. Okay, we substitute them, then we have A multiplied by tau 1 plus tau 2. Also, we had tau 1 and tau 2 here. This is our tau 1 and this is our tau 2. Substituting these values results in F force equals to A multiplied by mu1 capital V over H1 plus mu1 over A capital V, yes, over H2. Okay, and factoring out mu1 and V, we have A mu1 V multiplied by 1 over H1 plus 1 over A H2. Also, we had before H1 equals to H, capital H, minus H2. Okay, we had the information about the problem. So we have A mu1 capital V multiplied by 1 over H minus H2 plus 1 over AH2. Now we have the first step done. Force as a function of H2 equals to A mu1 capital V multiplied by 1 over H capital H minus H2 plus 1 over AH2. This is our first step. We obtain the relation between F and H2. Okay? Now, the second step is to take the derivative of F with respect to H2. And it's equal to a mu1v multiplied by 1 over h capital H minus h2 squared minus a over ah2 squared, and putting it equal to 0. As you may guess, this term is not equal to 0, and as a result, this term must be equal to 0. So by this we have 1 over h minus h2 squared equals to a over ah2 squared. Now, from this, let's do some manipulation. We have h minus h2 equals to ah2 over square root of a. And from here, we have h2 multiplied by square root of a plus 1 equals to capital H. Okay, now I'm continuing here. From here, we obtain h2. h2 equals to h over 1 plus square root of a. What's the problem's aim? Its aim is determining h1 over h2. I write this like this. h1 is h, capital H, minus h2, and h2 at the same place. And this equals to h over h2 minus 1. But what was h over h2? From here, h, capital H, over h2 equals to 1 plus square root of a. So what do we have here? This is 1 plus square root of a. So the final result for our question is h1 over h2 equals to square root of a. This is final result for the problem. There's a point here for this question. You should note that. Shear stress at the top and bottom surfaces of mid-plate are not equal. Tau 1 is not equal to tau 2, and velocities at top and bottom plate are equal to 0. No slip condition, as we investigated in the previous session. Guys, that's it for this session. Please don't hesitate to ask any questions about this topic, and you may find my contact information at the description. Thanks.